AP Chemistry, Unit 6.6, Introduction to Enthalpies of Reactions. Molar enthalpy, or delta H, is measured in kilojoules per mole. And for endothermic reactions, our delta H is going to be positive, and it can be sometimes written as a reactant. For exothermic reactions, our delta H will be negative, and it will sometimes be written as the product. Remember that endothermic reactions, we had to take in energy, and so that's why it would be written as a reactant, whereas exothermic reactions, we are releasing energy, which is why it would be a product. Oftentimes, molar enthalpy problems are written as an additional piece of a limiting reactant problem. So before you end up solving the overall heat absorbed or released, make sure that you determine your limiting reagent. Don't just proceed with whichever reactant you want and give that answer. There is a good chance that potentially you did not choose the correct limiting reagent, and therefore your problem would be wrong, even if you did all of the math correctly. So just be careful and make sure that you determine any limiting reagents that are there. So specifically for determining enthalpy, there is a specific type of calorimeter called a bomb calorimeter, and a bomb calorimeter is often used to determine the calorific values of foods. It's how we determine how much energy is within a food. I know that molar enthalpy is given in kilojoules per mole. However, our food is given in calories or kilocalories, capital C calories, and calories is just another unit for energy. And so we are able to convert the kilojoules into kilocalories, capital C calories, and that is what that value is on your food label, is specifically the amount of energy that is contained within that food. So for bomb calorimeters, they're the most common thing that we will use to determine the amount of energy that's within a specific food. And the actual bomb calorimeter is going to be filled with oxygen gas before the sample is ignited. And then the heat produced by that reaction, by the combustion of our sample of the food that we are trying to determine how many calories there are in, is going to be able to be determined based off of the overall temperature increase of the water that is surrounding the calorimeter. So here I have a diagram of a bomb calorimeter. And so we have our actual bomb calorimeter here. You can see that it is surrounded by water. We have a automatic stirring rod that's going in and is making sure that the water is evenly coming in contact with the outside of the bomb calorimeter and taking in any of that energy that is being released by the sample once it has been ignited. We ignite it via electrical impulses, so we have our positive and negative wires here, and then we have our sample. Remember that the bomb calorimeter is also going to be filled with oxygen, and that's what allows the combustion to take place. We also have a thermometer where we would have read the initial temperature of the water and then the post-ignition temperature of the water to determine the overall increase in energy that was absorbed by a known quantity of water, and that's how we would be able to figure out exactly how much energy was in that food, and therefore go ahead and determine the number of calories in that food.